Let me get started. Let me introduce YoungWoo So. Dr. YoungWoo So, it's been building robots in many forms for a very long time. He has a very distinguished career. He's currently Senior Director of Autonomous Systems Development at Hyperloop One.
Sorry, not anymore.
Oh, not anymore. That's what it says here. So,
Okay,
so
I
tell
know.
me where you are now.
Well, I started my own company.
Ah,
So, well, just if anyone happen to look for a new opportunity, just come to find me, talk to me. after the talk.
excellent place. But see, it says Hyperloop One.
Right. That was old.
Okay, great. So we're very excited. I am very excited actually because he's going to be talking about building a typical visual SLAM pipeline, which is, I think, a very interesting topic for all
Great.
of us. So please welcome.
Hi everyone. I'm YoungWoo. I used to work with the Hyperloop One, and now, just like I said, I started my own company. And today, what I'm going to talk about is building a typical visual SLAM pipeline. So, as some of you might know, SLAM is a huge field. So I wouldn't intend to cover all the detail about the SLAM, but what I'm hoping with this talk, give you a good overview of how visual SLAM pipeline typically built and good reference so that you can do your own investigation later after the talk. So let's get started. So what is a SLAM? SLAM is acronym stand for simultaneous, localization, and mapping. And this is formally, it is a problem of building a globally consistent representation of the environment by leveraging ego motion, compensation, and loop closure. So that's a formal definition. And mathematically, it has to solve a nonlinear least square. So, and then we will have to always deal with the camera trajectory. And basically what we do is, everything we represent as a point. And a point in the 3D we represent with location and orientation. So when I'm standing here, let's suppose I'm shrinking to the 1 point. And we can represent me with the 6 numbers at location and orientation, how I orient it and where I am in the 3D space. So we're going to represent the camera as a 1 point, and we're going to represent environment with a set of features, and each of the features has 6 different numbers. So what we want to do, and those numbers have to make sense with respect to the global coordinate. That's basically what SLAM tried to solve. And well, it is in fact, indeed, one of the activities we do occasionally. So when we visit department store, well, some of you may need a purchase the gift when you go back to your home. So you look around the department store, and you asking the people, actually collecting the measurement around the environment, and you remember something, and you keep look around. And while you're doing that, you actually build your own internal map of that particular place. This is what we typically do. So today, what I'm going to talk about is, how we actually do this and computationally. So, and this is the things you can find from the literature. And at the top left corner, this is derivation of maximum of posterior to solve nonlinear least square. And I have a slide to talk about this, but I don't think I have time going into detail. But like I said, I like to give you my slide as a good reference point for the later. So just so you know, I was told companies let you download all these slides you saw today and tomorrow, and after the conference. You will get the email, and you can have the link to download all these things. And on the right side, I have a bunch of graphs. So we can represent and we can solve the SLAM problem as a graph problem. So in the graph, each of node represent the feature point or camera pose, and then we can represent with the edges and how they relate to each other over the time or geometric relationship. And the left bottom, I have a couple of boxes, and it is explaining, it is describing what is typical building blocks for the SLAM with visual pictures or images or LiDAR, radar point. And so we have a front end, which actually does picture extraction and tracking, and a back end, and it does all the computation intensive tasks like a bundle adjustment, and those things happen in the back end. So this is a typical typical pipeline or typical building blocks for the SLAM. And so then why we actually do care about the SLAM technologies or SLAM technique or all the building block in the SLAM? Because anywhere, any application where the motion of the camera or motion of the object have to be handled properly. So all the technique I'm going to explain is going to be used taking care of this. And we're like, mapping localization, of course, and robotics. Robotics we have to keep track of the robot where it is with respect to the global coordinate, how we orient it in order to control so that it works autonomously to achieve the goals. And automotive, there's a lot of applications talk about automotive applications that we need handle this thing properly. So SLAM technology have to use properly to build a high definition map so that car can drive autonomously based on the command from autonomy. So this presentation, this talk, hopefully give you a good overview of how SLAM pipeline, or particularly visual SLAM pipeline, typically built. And I hope my slide can be used as a good reference point later. So that I'm going to use ORB SLAM. I believe it is one of the well-written, working well open source code and used many places. And I like to use ORB SLAM as a case, go over to explain the typical visual SLAM pipeline. So these next couple of slides, I'm trying to give you what is SLAM in a high level, very non-technical terminology. So let's say you are in the shopping mall and try to find something for your significant others. And you wandering around, and here I represent each of time step in discrete time. And then you are walk along and wandering around to find what is good for your significant others. And then while you're doing that, what you actually doing is, save or memorize certain features of the environment. Like here, one of the distinguished feature with others is like overhead or overpass or bridges if you are in the second floor. If you are in the first floor, it looks like overhead to you. And you will look at each of signs of the stores, and you look at and you kind of remember, and when you come back, you know where you were before, and now you're where you are before. So this process we actually does computationally to build the map through using the SLAM techniques. So let's look at the typical visual SLAM pipeline. So this visual SLAM pipeline I am going to describe today is based on visual picture extraction. So there's other techniques like DNN-based or direct method without extracting pictures, without rely on the picture point. But today's talk is based on the picture, particularly visual picture extraction and tracking based SLAM pipeline. So we have 4 different, so I'm looking at the left side, 4 different big building blocks. First thing what we need to do is extract the pictures. So I'll describe what the picture is and how important they are, how we can extract that later. But picture is a computational representation of a point in the image. So, and once we extract the pictures, we have to have a match or tracking that picture over the time. So that picture tracking actually gives us correspondence between correspondence of a picture over the time on different image frame. So that gives us good information to estimate how my camera or the rigid body has a camera on it has moved over the time. So once we have that, we have some information or evidence, we can do the estimation of the pose. So again, pose, I told you earlier, pose is 6 degrees of freedom, has 3 parts is about the location, and the other part is orientation. That's the way we represent a rigid body in the 3D dimension. And then once we have a pose estimation, and later what we need to do, and we need to find the more constraint to complete SLAM pipeline. That is loop closure part. So ORB SLAM has roughly these steps. So I intentionally divide by, there's many steps, many building blocks in the ORB SLAM open source, but I divide by intentionally corresponding to the typical SLAM pipeline. So they using ORB features. That's one of the way, one of the algorithm you extract the picture from the image, and they extract the ORB features, and they matching or tracking that picture over the time. And then once they have that, and they try to estimate camera pose, how camera move by analyzing multiple camera over the time. That's what they do usually for the pose estimation, camera pose estimation, or camera motion estimation. And then within the certain local frame range, say, for example, from first frame to the 10th frame, they do bundle adjustment to solve the pose estimation with more constraints. And then they do later and detect the loop, whether there is any certain place visit earlier, and then once they detect that, they do the global bundle adjustment to complete the SLAM test. I will going over each of them detail. Later slide. So what I just described, and this is actual building blocks, component for ORB SLAM, and I colorize based on what I just told you. I have at the top tracking part, which is the feature extraction and tracking all the time. And we have estimation that actually does building on local maps using bundle adjustment. And then at the bottom left, and I have 2 big blocks, which does place recognition and the loop closing. That actually does loop closure as a final step to complete a map. As a result, they pull out a bunch of map point. Map point is the visual picture on the environment, and the key frame and the frames, image frames that hold a bunch of map point. And then based on this, and they will output the map for the environment. So that's an overview of typical pipeline. So the visual pictures, the picture in the computer vision and multi-dimensional representation of object or part of object is typically focused on particular point. Okay, so that is, and it is purely numbers in the computer perspective or algorithm perspective, and hopefully that picture is visible from one image to another. So the picture extraction method should be able to take care of the variance of illumination or scale changes and other appearance changes, so that once we have pictures extracted from one point, one image, and then we should be able to find that pictures from other image in the other time, as long as they visible each other from that perspective. So that's the digital pictures. And we like to have picture detection invariant to the illumination or appearance changes. So the way we extract, and it all depends on what kind of algorithm we use. There's many algorithms, many others, and they have all their different features, different properties and pros and cons. And if you want to understand, if you want to have a really, really good understanding on the visual features, I would recommend these two papers. And they talk about the scale space, they talk about the different property of good feature should have. And so what makes one method better than the others? Like I said, invariance in appearance changes. So appearance is changing based on where you take the pictures, and scale is going to be changed, and orientation, illumination will be changed. So we want to have an invariance on those changes so that we want to see the same point from different perspectives. So what I recommend, so ORB is a good picture representation because it is fast and it has decent invariance to the appearance changes. So what does it look like? So this is actually learned a couple of feature extraction algorithm using open source code like OpenCV. And I have actual code put it into this slide so that you can use that later, but it's pretty simple. It just couples lines of code. And so you can extract from this given image to the left, you can extract ORBs and those features. They have different characteristics and properties to take care of certain situations. So this is another example of picture extraction, and I use for this example, I use Kitty dataset, the dataset from autonomous driving effort from Germany. And they release this data set so that other people can use for their algorithm development. And I applied one of their images to these techniques early on, and these are the results. So the picture extraction is all depends on your need, but you have to try out multiple things whether any particular algorithm works for your case. So once we extract the pictures, we have to track them over the time. So in for example, let's say you have camera giving you 30 frames per second, and you are driving in the highway, and you see one frame, and the next second, based on your speed, for example, if you're driving 60 miles per hour, and you are going to be a couple meters away when you get the next images. And then if we extract the good pictures, that picture should be available next frame, and then you track them so that you correspond those two pictures from different images but the same pictures. And once you have that, you have a tracking result. So why we do that? And that's going to give us how the car, in my example, or your case, your camera or phone, moved over the time. So the way we do, it depends on your need, but typically we use OpenCV built-in functions. They have good APIs on the 3D registration, and those are the things you can easily pick it up. So if you're looking at, this is example I learned OpenCV code, and I have two different images, and the image has a full size of the box, and the other image has that box is with other boxes. And then we extract the pictures and then try to match which one correspond to the others. So this is what we want to do, what we want to see in the real applications. So I'm not going to go into details how we actually does, but what you see in the left, this is a Python OpenCV interface, and the one at the right is the C++ code. They don't have a long line. It's pretty easy to use. And if I show you the kitty data set example, this is the way we extract and track picture over the time while car is moving forward. So another example of picture tracking, this is the frame-by-frame visual odometry. So the visual odometry is estimating odometry of the moving object, just analyzing image on that object. So what I did here is I used the past pictures. So past is another picture extraction algorithm. I use that, and then I use KLT, Lucas Canade tracker we heard this morning, and I use that to track the picture over time so that I can estimate where this car drives. So what you see on the right side, this is complete odometry result. And what you see in the big image, that is one of the picture tracking results on the one image. So I think I gotta hurry up a little bit. So, and then once you have picture tracking and you have correspondence of picture you see in the previous image and the current images. And that's gonna give you a bunch of cue how your motion evolved. So the camera motion estimation or pose estimation actually solve with that correspondence to solve 6 degree of freedom parameters about the pose. And so this equation is not meant to be ongoing detail, but I'm just giving you a good reference. And this is a typical the way we project a point in the 3D to the 2D image plane. And as I mentioned earlier, so SLAM, each of block actually solving the nonlinear risk scale, as you see in here. So the bundle adjustment is solving about the same problem, which is minimizing the error between the point you see in the image and transformation, or the way you project that 3D point into 2D. So if you try to minimize those, you understand clearly how this point is generated. So that's the idea behind the bundle adjustment. And then they using many points. And earlier, pose estimation just tried to solve camera movement, plus bundle adjustment tried to solve camera motion and the point in the environment. So that's the big difference. And so the way we solve, this is a derivation of nonlinear list scale. And so because it's nonlinear, we can't just solve one shot. And so we need to have an iterative solution for the optimization. And that's where we have to use this delta for the iterative optimization. This is another example of a bundle adjustment, and which this is from one of the latest paper we published. And so if you do bundle adjustment with all the measurement, you can get a pretty decent output. As in here, the red dot is ground truth, and the blue dot is initialization at the left, and the right side is output. Okay. So the last step, what you need to do is loop closure. So loop closure is actually detecting point where we visit earlier, so that's going to give us a lot of constraint to solve optimization better. So that's what loop closure is about. And the way they do, they need to detect loop closure, they need to detect the loop first. So the way they detect the loop is, simply, and given particular image, and try to pull out the dead image, whether I've seen this before. It won't be exactly the same image, but the landscape behind, or the content of the picture should be similar. So the point of detecting loop is pulling out that image so that we can put a lot of constraint to solve earlier optimization problem better. So this is just giving you another example of loop closure, why we do that, what is the result. And so, so once you have a pipeline, and you should be able to evaluate how good it is. And that is done many ways, but one of the ways you can do is you pull out the ground truths. Ground truths can come from using other data set, like inertial measurement from IMU or other data, fusing them together with a visual image, and then you pull out the ground truths. And once you have a ground truth, and you can measure the performance just looking at, for example, root mean square errors, errors between what you output and what ground truth said where it should be. And then you try to look at the numbers. That's the one way we can evaluate how good your pipeline is. And there's a lot of open source packages available, and these are the one mostly used. And so you can check it out. And dataset, there's a lot of good dataset. The earlier talk about, you're not going to rely on completely open source dataset or open dataset, but still it is a good starting point. And there's a lot of good starting point. One of that I show you is Kitty dataset. So the challenges, I'm going to quickly go over these challenges. So challenges, building a SLAM pipeline, and particularly visual SLAM pipeline, is appearance changes. So when you take pictures in different time and different pose, they always give you different images of the same object. That's the big issue. So the appearance is the problem, and particularly this is the problem when you try to build SLAM, and SLAM on the environment doesn't have much distinguished features. If you're looking at the corridor, and they don't have much, distinguished feature unless you see the doors and others. So, and then outliers. And earlier I talked about, the picture tracking, and that picture tracking assumes the correspondence estimated correctly. What if it is not? What if I said the one point I saw in previous frame, and I matched to that another picture, which is not same picture I saw earlier, and how that's going to affect to the pose estimation performance and the optimization performance. And the map representation and time baiting and deformable object, they are all about the appearance changes. So, and then once you have the good map and how you want to update the map. So hopefully, mostly map is about the static environment, won't change much, but occasionally you need to update to reflect the changes. So, in summary, sorry, I'm running out of time. And I hope I give you a good overview about, typical visual SLAM pipeline, how they built, and my slide will be used later for the reference. If you have a question, you can ask now or let me know later to send me the email. Thanks. Sorry.
Thank you very much. Very interesting. We are running out of time, so we have probably time for one question. There are microphones in the aisles, so if you have a question, please come to the mic. Or YoungWoo is going to be here after the talk, so you can talk to him. I have a quick question.
Sure.
Can you give us a sense of the computational requirements for implementation?
That's a really good question. It depends. It depends on a lot of parameters. Let's say, if you want to track many features, that's going to increase your computational resource, computational need. But that is needed because we want to have many features tracked so that we can estimate, we can collect more evidence about the motion. But at the same time, you increase the computational resource. So, typical case, if you use laptop with Intel Pentium 7 with a 3.2 Hz with a 16 gigabyte, you learn ORB SLAM real time with about 100 features. It's going to give you pretty decent performance.
Great. Thank you very much.
Question?
That answered my question. Thank you very much.
Thanks. Thank you.